Okay. Fan, please switch off your mic. Thank you. So if this is an outlier, and if you throw away, if your errors go within the tolerance limit, but with this, the errors are slightly beyond the tolerance that you have set, okay, then you throw the data point away. Okay, but then what happens always is, let us say whichever model we use, and as we collect more and more data, at some point we are going to see that the errors start breaching the tolerance, the bounds we have set. When that happens, you go back and redo the entire exercise, build the model once again, okay, starting from scratch. So that's the approach I would take. So to answer your question, data is sacrosanct, it's primary. To throw away a data point or not is usually decided by this two-step approach. See whether the data point is an outlier by these traditional tests. Then ask this question: if retaining this data point, do I get more errors? Or throwing away this data point, do I get more errors? Okay, and whichever model is better, use that model. That would be the approach I would take.
Thank you, sir.
Okay. So the next one, yeah, go ahead.
Can you repeat that again?
Sorry. Okay, you use the word tolerance. I know it should be obvious, but tolerance meaning the tolerance of what?
Tolerance for the error. Let us say you are going to predict some kind of impurity in your samples. Okay, let's say you are a silicon wafer manufacturer, and you are predicting the impurity in a batch, okay, percentage of impurity. So you are going to say, not percentage, you probably measure that in terms of parts per million, right? So now what you have done is you have measured, you have taken some samples, okay, 15 samples from the assembly line, and you have measured them, and then you are making some predictions, okay, something. And in that 15, the sample of 15 items, one of them you think is an outlier, okay, and now you ask the question, okay, retaining this, does it give me an accurate value or change the model if I throw this data point away? I have a model. If I throw this data point away, my model changes by some amount. What do you mean? Your beta naught values changes, your beta 1 value changes, that is the parameters of the model, and also the residuals changes. The residuals also change. Okay. Now you ask the question, okay, residuals have changed, maybe they have worsened, or maybe they have improved. If they have worsened, okay, you are tolerable. Whatever be the errors that you get, whatever be the impurity measurements you have, as long as your predicted impurity values, okay, are within the measured impurity value. So you have this measured this thing, you also have your model, and your model has predicted some number for the impurity, and you have this measured impurity values. If that error is within your tolerance, okay, I want the model's prediction to be within 1 or 1.5 parts per million. Okay, 1.5 parts per million. That's the maximum you can tolerate. Your measured value is 6 ppm. Okay, therefore your model can predict anywhere from 4.5 ppm to 7.5 ppm. If it is within that range, I'm okay. Okay? If that is that's what I mean by tolerance. That you said, it's subjective. It varies from from problem to problem, and it comes from domain expertise. Okay, say for example, if you're going to predict some kind of GDP change in the next quarter, okay, and we are talking in some percentage points which are usually small numbers, 0.25% or 0.5%, and there if you want to make a prediction, we are going to have a very tight constraint there. But let's say if you are going to predict the number of passengers who are expected to take this metro line in the next week, average passengers in this metro line for the next week or next month, whatever, okay, daily value. On an average, that might be a few 100,000 people taking this metro line. And there your tolerance might be like, okay, I'm fine as long as the number is within 10,000, right? So that number that you're going to do, the tolerance you are going to set, that is the difference between the prediction and the actual measurement, how much error is agreeable, that you are going to set based upon your understanding of the domain. Okay, now
Thank you. Thank you.
Okay, so sir, so basically in the finance, we generally prefer to have an alpha value, which you have just mentioned that 5%. That it depends on my appetite, that how much risk I can take with the sample of the data that I'm bringing in for the research, right?
correct.
That's the one thing. And the second question regarding this leverage, because here we have one input and one independent variable and another is a dependent one, right? But in case if I'm having a multiple independent values, then how I would proceed? Because here we have only one input, right? So I would like to understand if you can bring some light on that. If I'm having multiple inputs are there.
Well, that's a very, very difficult question. Okay, so what you will have to see is you will have to look at each variable independently, okay, and see if there is any effect of these variables, and whether a particular data point is going to be an outlier on some variable. Let's say you have 3 variables. Okay, there is one data point which is an outlier on one variable according to leverage, but not on any other, and every other points are within that leverage, within less than 2 h bar on each of these independent variables. If this is the case, how do we deal with it? Okay, the question is that you will have to do the same thing, drop out that point and redo the model. But when the number of variables is very large, okay, let's say we have like e-commerce store, let's take Amazon. Okay, they might have 10,000 variables. If they want to predict how much is a particular customer going to spend next month, okay, they might have 10,000 variables to deal with. Okay, how do we deal with it? If you want to really go by this method, then yes, you will have to use this. Okay, you will have to check for this.
Yes, sir. I actually, my question actually came from an idea that generally when I, predict these stock prices, there are multiple factors that I need to consider. And this is something that very interesting topic that you have, covered in a couple of classes. And to be honest, this is something where I need to apply, and my knowledge here, it's very less. And that's where I need to go and try this method and see if I could find out the outliers across other the variables and the features that I have. And to be honest, I haven't applied it before. So let me find out that what kind of benefits I could get on this.
Yes, and I'm okay. I'm going to kind of go ahead, get ahead of myself and say something. Okay, when we have large number of variables, okay, we are going to look at much more powerful techniques, and where we are not even going to look at these ideas. and we are going to talk about them in a couple of sessions. These are important ideas, and these are very useful when you can actually use these ideas. But when you have too many variables, and you can, in current situation, you could easily write a code for that, and the computers can do these things within a fraction of a millisecond, no problem. Of course, if the data is also large, okay, if you're talking about Amazon or something like that, the data also probably they have a few billion customers with 10,000 variables, then it's going to take it might take some time, but it's not impossible to do this. So theoretically, this is possible, but there are also other powerful techniques where we are not going to worry about these things and just apply those different techniques and solve the problem. Okay, that we are going to get to that in the next couple of sessions. So until then, please hold your horses on this one. And the question that you are asking, especially regarding stock price, I do not know whether you are going to predict stock prices or stock movement. Okay, price point prediction for stocks is going to be very tough. Movement is probably a little bit less tough, in my opinion. Okay, but price prediction is going to be extremely tough because the randomness of the data, the number of variables. About a few years ago, one of our colleagues, he used to be one of these people who worked. He did a PhD in physics. Okay, you could check for his name, Anandan Jayaraman. He was a theoretical physicist, and after his PhD, in fact, during his PhD days, he came up with an equation which bears his name, his and his advisor's name. Okay, so somebody Jayaraman equation. Okay, so such a brilliant mind, and he moved to, after his PhD, he moved to finance. He worked a lot on algorithmic trading, and by his one of his estimates, to study the movement of stock, the movement of stocks, he figured that of the order of 213 variables he had identified that needs to be included in the models to get a fairly good, accurate prediction of the stock movements, okay, or prices, maybe prices. So that's what he did long time ago. Okay. And dealing with these kinds of variables is very difficult, because the kind of data that you are dealing with is called time series data, which we will again get to maybe 3-4 sessions from now. Okay, and the kind of specific problem you are talking about when you're talking about independent variables in relation to stock movement is a much complex task in stock prediction. Okay, we'll talk about them when we talk about time series analysis. So until then, please hold your questions on that. No, but start thinking along these lines. These are going to affect your models. That's very much true. Now, we looked at only the.
Thank you.
We looked at one. Thank you. Let's move on. We looked at only the independent variable. Right now, we are dealing with only one independent variable. Okay. What about the model prediction itself? Okay. Can that, or the errors in the model, no, can that tell us something about a particular data point? Okay. Remember, the measured value we are saying is nothing but this beta naught plus beta 1 x plus that epsilon. So during some measurement, there could have been a large error. Where it came from, we do not know. That's a random error. Maybe that could make a data point an outlier, right? So in fact, I think I saw a comment somewhere that somebody said, that was a very, very intelligent comment, and that's where we are moving. Yeah, John Sirani Murugesan, large error plus high leverage, and then it's dangerous. Yes, it is. It is. And that's what Cooksby talks about. Okay, so the effect of errors is captured by the studentized residual. Okay, studentized residual, as you can see, it is nothing but the residual error divided by mean squared error. Okay, that is the variance of this square root of mean squared error. So divide by the variance. So again, what we have done, take the error value, divide by the standard deviation. Square root of the mean squared error, that's the standard deviation, right? So that's the standard value for the error, Z score or Z score for the error. But we are not taking a simple standard deviation. We are taking a standard deviation, also factoring in the leverage. Okay, why? Because if you see a large error in the middle point, okay, will have probably a less effect than a large error in an extreme point. Okay, if this point is much farther down and this point is above this model by the same amount, okay, the effect of this point would be much higher on the model than the effect of this point, the central point. And that is why we bring in the leverage also into the definition of the studentized residual. Okay, so essentially what we are doing, we are kind of modulating the standard deviation of these errors by the leverage itself, and then taking the standardized score for these errors. That's what we are doing. So when we do that, for example, for this fictitious data point, this is what we get. Okay, this first point we have something, second point, blah blah blah. Okay, and okay, so what? So we need to figure out if any of these numbers is a large number. If any of these numbers are large number, this is a studentized, as I told you, this is studentized, or sorry, standardized. It's a Z score, right? Z score means how many standard deviations away. We know if it is 2 standard deviations away, then it's beyond the 95% confidence interval. It's that less than that 0.05. Okay, therefore we set the threshold of 2, -2 or +2, -2 if it's negative, +2 if it's positive. Okay, or the absolute value of the studentized residual, if it is greater than 2, then we call that as an outlier. In this problem, you see none of these points is an outlier. None of these points is an outlier. Okay, let's take a look at our favorite grocery delivery. Okay, so we need to have this EI. We need to calculate this. Okay, so y hat predicted value. We need to get the predicted value. We had that somewhere here, right? Y hat predicted value. Yes. Control C. Oh, why just that? We'll have both of them. Control C. Predicted value. Numbers. Predicted value. EI is a byte, right? So this is what we need. And then I don't care about whether we are going to use them or not. I'll just copy and paste. Okay. Obviously, EI, some of them will be 0. The addition mean value will be 0, but the standard deviation will be different, right? So that's what we got that here. Okay. Now for each of this, we are going to calculate R sub I. So how do we do that? That is the residual divided by square root of the we have standard deviation, so we need to mean squared error. So that would be okay. Let's do something like this. Okay, I'm going to do this. What is this? This is okay. Times square root of okay. I'm standard deviation, right? So therefore, I'm going to do standard deviation times square root of 1 minus leverage. leverages here. Okay. So I got RI for all this one. So let's do this. So I got an RI for all of them. So let me do this. Control C, Control V, it doesn't matter. Now I'm going to do outlier. Okay. What is it? It's the same thing. If the RI, okay, is greater than, okay, let me see, absolute value of this student residual is greater than 2, then it's an outlier, otherwise it is not. Okay. So you could see in our data point, there is one point which is greater than 2, which is this, again, the same point, right? The last one. That's an outlier. So definitely this point is going to be an outlier. Okay. But in this example, it is not clear whether this data point is outlier or not, because leverage says it's outlier, but student residual says it is not an outlier. So what do we do? So now what we do is we combine both of them, the leverage and the student residual, we combine them in this very complicated formula, okay, and then determine what is called the Cook's D. Okay, this is the studentized residual squared. This is the leverage. Okay, don't worry about the formula. We are just combining both of them, leverage and the studentized residual, and then 1 over P. That means we are thinking on an average, how much does one parameter contribute to this quantity? That's what we are looking at, right? It's taken with respect, average taken with respect to the parameter, number of parameters. So we calculate this Cook's D. Don't worry about the formula. It's just a combination of this. So when we do this, okay, the Cook's D, and what is the, now we do not know what Cook's D, you know, for leverage and for student residual, we were able to kind of guess what is going to be the threshold to determine an outlier. In this case, it's not obvious, so I'm going to give it out as a statement. Okay, any point which has the Cook's D value greater than 1 is considered an outlier. So you see in our example, this point, the 5th point, okay, it has a Cook's D value greater than 1. Okay, so that point is considered an outlier. That's an outlier. Okay, that's well and good. Okay, so that means we need to drop this point, build a new model and use it. Build a new model and use it. So if it's an outlier, you drop that point, okay, and build a new model, use it. But then it's not over there. That's another guideline, namely, in the other points, no, in the other points which are not outliers, identify those points which has Cook's D value greater than 0.5. Right? Find the data points which have Cook's D value greater than 0.5. Those points are considered potential outliers. Okay, in this case, we have this one point, which is the first point. That's a potential outlier. So what do you have to do? An outlier, drop it. This is the standard guideline. If it's an outlier, drop it and go on and build it. My opinion is not that. My opinion is check it actually. Okay, because every data point is sacrosanct. So I would be cautious. Okay, but what this tells you is, if you drop this point, your model is definitely going to change. That's what this Cook's D tells you. Okay, but then for this point, for this first point, we are not sure. Okay, it's a potential outlier. So what we do is we build another model. Okay, drop this point and see whether the model changes drastically. If it does, then you have to drop this also and use only the remaining points and use that as a model. If dropping this potential outlier does not change the model much, then you just keep using this model. Okay, retain this point and use this model. Yes, Prince Dubey, please go ahead and tell me.
Model does not deals with the negative data as well, because here it is considering that anything which is greater than 0.1, 1.0 needs to be considered as an outlier. But what if my number is less than 0.
No, see,
minus 0.
or is the only thing that can be negative or positive. We are squaring.
Okay, sorry. I didn't see this. Okay, sorry.
Leverage is
sorry.
positive. Here, there's a possibility that HI could be greater than 1. But it never happens. Why? Because the value for HI, okay, the sum of all HI is equal to the number of parameters. If you have a large number of data points, that means each HI is going to be less than the number of parameters divided by that number of points. Therefore, this is also going to be positive. P is a positive number. So this is always going to be a positive number. Okay. So that's the answer. So now let's go ahead and ask Cook's D. Cook's D. What is Cook's D? Cook's D is equal to 1 over 2. In our case, it's a 1 over 2 into this R squared into the leverage. Where is leverage? Here is the leverage divided by 1 minus leverage. Okay. That's it. Cook's D. Let's see. Cook's D. Right. And let's check all these things. Obviously, you see the last data point is greater than 0. Is greater than 1. Therefore, that's again an outlier. So you can go ahead and ask outlier. If Cook's D value is greater than 1, then outlier, otherwise no. And okay, obviously this also is not right. So this is what we do. What I want to say is, okay, why am I demonstrating this silly data set, this grocery store data set? According to, yes.
If some algorithm say that factor is an outlier, but another say that this is not, what should I do?
No, here we are just using only one algorithm, right? The algorithm is a Cook's D value. That's all we are using. Okay, when you say algorithm, let us say you are using a linear regression model, if you call that as an algorithm. And in that model, using that model, we got this Cook's D to be high. Therefore, this is outlier. And another algorithm you might use is something called let's say, decision tree algorithm, or something called some other algorithm. Let us say decision tree or neural network. If that's what
I'm sorry, I'm not mean algorithm, but I mean the method of calculate of identifying that is an outlier.
We would see there are 3 methods of identifying the outliers. One is the leverage, right? So this is one thing, leverage. The other one is the studentized residual, which is this one, and then Cook's D. Cook's D is your ultimate go-to, right? Cook's D is the ultimate go-to. So you check for Cook's D. Okay, and if Cook's D says it's an outlier, it's an outlier.
Okay, got it. Thank you.
Yeah, sure. Now, why did I deal with this particular data set? No, it was very obvious this is going to be an outlier. Okay. The problem is you remove this. So I told you, if it's an outlier, throw the data point, rebuild the model with the remaining data points. Okay. When you do that, everything will be fine. And when you do all these tests for assumptions, everything will be fine. And finally, when you come to outlier testing, you will find one data point as an outlier again. So you remove that also. So now you have only 23 points. We started with 25. Remove this with the remaining 24, build the model, You find one outlier, remove that. So build a model with 23 data points, do this thing, you'll find one more outlier. So any number of times you do this, okay, I once I put this in a loop and I went up to 8 data points. Okay, when I went down to up to 8 data points, and every time I found one outlier. Every time I found one outlier. Okay, so even though this looks like a very funny or contrived example, the contrivation, I do not know what the correct word is remarkable that this kind of an example comes out. Yes, Mohammed Niaz, go ahead.
Finally, when we remove, iteratively the outlier, the dataset itself would have become an artificial dataset which doesn't have the natural behavior reflecting.
Exactly. So this gives you a very important clue that your approach is not working. Right? If the data is sacrosanct. Okay. So every time when we keep doing this, if something is going wrong, it tells you that your approach is wrong. So what could be the mistake here? There are two things that are possible. One is I have to, even though everything looks normal, and this issue tells me maybe I should go search for a transformation. No, I should look for a transformation. That's one thing. But much more plausible is that this single variable is not sufficient to explain, to deal with the delivery times. Maybe I need more variables. Okay, that's another thing this one suggests. Okay, so that's why I like this example specifically because of this particular thing where it naturally leads you to the question, what am I doing wrong? Everything seems to be okay, but then why is it failing again and again and again? Maybe because we are missing something, and what we could be missing is additional variables. Okay, so this is what I was talking about. When you have if the data remains like this, then you don't have a problem. But what you would actually find is your the moment you, or maybe when you have this point removed, your data, your model could actually become something like this. Right? No? It could become something like this. No, it will become something like very different from the original one. Okay, so that's what I was talking about. So this brings us to the end of simple linear regression. So what is it? Build a model, but that look for R squared. For a simple linear regression, you don't even have to look at R squared. You look at rho, correlation coefficient. Square of the correlation coefficient is R squared. So before even you start building the model, you already know how much of the total errors you can rectify with a simple linear regression model. Okay, so that you got that already. But then you go ahead and build the model and then see whether the model makes predictions different from no model. Okay, how do you do that? Check for the F statistic, and the F statistic passes. That is, if the p-value for the F statistic is less than 0.05 or whatever alpha you have chosen, then the model is usable. Then go ahead and check whether the parameters are agreeable. How do you do that? Look for the p-value for the parameters. The p-value for the parameters are determined using a t-distribution. Look for the p-values. If the p-values are less than your alpha, which is usually 0.05, then you use the p-values. You use the values that you obtain because the hypothesis is the parameter value is actually 0. You reject that null hypothesis. Therefore, you start using the p-values. You start using the parameter values when the p-value is less than alpha. So now with these things, you are okay. You strongly believe that your model is usable. But then now we go ahead and check. Okay, let's check whether the assumptions behind this model building exercise are valid. So you go check for all those assumptions. What are the assumptions? You check for the independence of measurements. How? Look at the residual plots. There should be no pattern in the residual plot. If that is the case, yes, independence of measurement is valid. Check for the linearity of the relationship. How? Again, there should be no pattern in the residual plots. If that is the case, yes, linearity assumption is also valid. Then go check for the homoscedasticity. How do you check for the homoscedasticity? See whether the range over which the errors vary, does it remain uniform, or are there big differences in the residual plots? In some regions, the errors are tightly packed. In some other regions, the errors are very loosely packed. If that is the case, then homoscedasticity fails. Okay. Then you go check for normality using the QQ plot. Okay. And if any of these fails, any of these assumptions fail, then what you do? Go do some kind of a transformation. To actually rectify non-linearity in the data, you use Tukey's quadrant and ladder approach, okay, and do the transformation. For other things, no, look closely whether there is possibility of any non-linearity, and that will usually guide you. Otherwise, systematically try different transformations and come to the best possible transformation that you can use. And finally, outliers, see whether there is any point that could have unduly influenced the model. How do we do that? You do that by looking at the Cook's D value. If the Cook's D value is greater than 1 for any point, then that point is considered an outlier. So remove that point and rebuild the model. If you have any data point with Cook's D value between 0.5 and 1, then that point is considered a potential outlier. If that is the case, you do two things. Build a model with that data point included. Build another model by removing that potential outlier data point and see whether the 2 points differ very much. If they differ very much, okay, oh, this is not going to be the good model. This is the model that we are going to get is something like this. Sorry, I just noticed. Okay. Yeah, I just noticed. This is what we are going to get actually. Okay, now if with the potential outlier and without the potential outlier, if the models are different, then you know that those potential outlier points are actually outliers. Therefore, throw them out and use the model without those potential outliers. Okay, so this is how we systematically approach simple linear regression problems. Okay, and simple linear regression is very simple and is usually simplistic in the sense that most real data do not come with only one independent variable. Many times data comes with many independent variables and one dependent variable. And that situation is called multiple linear regression. Okay? That is regression built with multiple regressors or independent variables. And that's where we are moving next. So we will deal with the multiple linear regressions when we come back after a short break. Now, the time on my clock, as you can see at the top, is 7:48 p.m. Okay, so in 12 minutes time, we will come back and we will start looking at multiple linear regressions. So once we understand multiple linear regressions, then we have understood linear regression in full detail. Okay, and that's where we are moving towards. So short break, we will be back in about 12 minutes time, and then we will try to wrap up multiple linear regression if possible today.
Crazy. Yeah, well, not crazy, but it's just intense. Neat. Technique. And it's all like this is like for me, it's like. Oh. Testing. Testing. Crazy. I was muted and I could hear myself, right? You heard that? You hear yourself or mean hear yourself? What was that on? I was using like usually I use my headphones. Oh. Oh, you were on that for the class. So I was on it on my phone.
Hey,
on-
Jeff,
on-
you might want to turn off the volume, mute yourself.
Trying to figure out how to do that.
So now what we are going to do is we are going to expand on the same ideas, except that now we are going to have more than one independent variable. So what remains constant, okay, from before? That's a very important thing to know. What remains constant is that the task is to predict the value for a variable, the value being a continuous value. It's not a categorical value, it's a continuous value. So that's a constant. When you have more than one variable in the on the independent side, right? So we have, let's say in this case, this is an equation where I have written beta naught, beta 1, x1. X1, the way I have written with the parenthesis means is the first variable, this is a second variable, this is a third variable, so on and so forth. Some people write with the parenthesis, some people write without the parenthesis. So I might shift between these two notations, but essentially means these are different variables. Okay. Now, when we have more than one variable, that is two or more independent variables, there are multiple challenges that arise. Okay. There could be some of these or all of these variables could be categorical. In fact, even when we have only one variable, this could be a categorical variable. For example, let's think of the situation where we have heights of people. That's the independent variable, and the dependent, the dependent variable is heights. Okay, and the independent variable is the gender. For simplicity, we'll have two genders, male and female. Okay. So when we have such a situation, that is the x variable is gender. So it's a categorical variable. It can have only two values, male or female. Okay. And then we have the dependent variable. The y variable is, let's say, height of the person. Okay. Now, can we build a model in that situation? Is it possible to build a model? How would we go ahead? How would we go about building a model? What do I mean by building a model? Essentially, I want to make predictions when some new data arrives.
How many variable?
There is only one variable, and that variable is the gender of the person.
Linear regression.
How do we do linear regression? That's my question.
Because you have only one variable to be x. So y
Yes.
equals to mx plus c. That's one
Correct.
linear. It's not multivariable yet.
That is correct. But c is a mx, x is a categorical variable, either male or female. It is not a continuous variable. It is a categorical variable. So how would we? So what do we do in this situation?
Do we bring the categorical variable out and build two separate equations because they're mutually exclusive in a way?
They're mutually exclusive. That's correct. Where is the equation now?
No, I mean,
there is no equation, right?
So
no
in the case of category variable, can we not do the encoding first and convert them into a numerical value, and then we apply the equation?
Okay, I have only two values for x. 0, I'm going to use the number 0 when the gender is male, the number 1 when the gender is female. So what happens because of that? Let's think about this, okay? What is it that I want? a new person walks in, and I determine that the person's gender is male. Now my task is I need to predict the height for this person. What will I do in this case? That's a task, right? That's what our model is about. So what can I do in this case?
Another equation.
There is no equation here. That's the thing. So I have 100 people in my data.
Enough data. It can't be done. It's not enough data.
Say it again.
What we can do is, sorry, maybe what we can do, we can put first all the second gender value as like 1. Then we can see. After that, we can also put other. So, for example, earlier we will put male as 1, and then first we will calculate. Again, we can put the male as 0. Then we can calculate, kind of like.
Let me ask another question.
The range of error is going to be too high. The range of error is too high to just use one
Yes,
variable.
the range of error is going to be too high. That's very true. But I am asked to give a prediction. What will I do in this case?
It'll just be the average.
Average of what?
Average of heights. In the
Heights of
data.
what? I have a data of 100 people. 40 of them are male. 60 of them are female.
Yeah, the average male height of the male and the average height
That
of the
is
female.
all. Correct. That's
it.
all. So, what, as he said, all you have to do is separate the data into different categories and just give the average value for each category. If a new data comes in belonging to one of these categories, the prediction you are going to make is the average value for that category. That is all. And there is no within quotes model building here. The model building becomes tricky when we have situations like this where we have more than one variable, where both the variables are categorical, or one variable is linear, that is, one variable is continuous, and the other variable is categorical. Then it becomes a little bit tricky. Okay, so how do we deal with that situation? That's a question. If there is only one variable, and if that variable is categorical variable, all we have to do is separate the data into these different categories and then make calculate the average for each of these categories and give that as the prediction for that category. So when a male walks in, take the average for all the males, give that as a prediction for this person. If a female walks in, take the average for all the females in our data, give that as the prediction for this person. That's all. So very easy task when there is only one variable and if the variable is categorical. It becomes complicated when we have more than one variable and then all or some of them are categorical. Okay? If all are categorical, again it's easy. Category 1, category 1. Category 1, category 2, category 1, category 3, category 2, category 1, category 2, category 3. Like that we can build those combinations. That's called the cross product. And then give that, let's say, for example, you have two variables, gender and educational qualification. Okay, so the educational qualification could be something like higher secondary, undergraduate degree, postgraduate degree, doctoral degree. Okay, undergraduate degree, master's degree, doctoral degree, and the higher secondary, 4 categories. Now, if you have enough data, you can do male higher secondary, male undergraduate, male postgraduate, male doctorate, female higher secondary, female undergraduate, female postgraduate, female doctorate. You can split these categories, right? Now, for each one of these, calculate the mean, keep them ready. When a female master's walks in, give us the prediction, the mean for that particular category, female masters. That's all. So it's very easy conceptually. Where it becomes difficult is when one of them, we have age as one variable, gender as the second variable. Even here, it is conceptually very easy. What do you have to do? Separate out the data into male and female, build one model for the males, build one model for the females using only the age. That becomes simple linear regression for males, simple linear regression for females. A new data point comes in, a woman aged 44, then go to the woman category, use the model you have, use that to make a prediction. Okay, so conceptually it's a very simple idea. Can we simplify it much further? Yes, we can do that, and that's what we will look at in a short while. What if all the variables are related to each other? We say these are independent variables, right? Independent means they are not related to each other. But what if something is related to another thing? If x1 is related to x2? Okay, so that's a possibility, right? How can we? I'm not able to think of a good example, but perhaps you can think of it this way, right? If people of different educational qualifications are there in the data, and in general, we would expect higher educational qualification to be related to higher age, right? In general, you are not going to expect somebody aged 17 to have a doctoral degree. Of course, you could have outliers, okay? But somebody aged 17 could have a higher secondary, maybe even an undergraduate degree, okay? Of course, somebody aged 65 could have had could have stopped with higher secondary education. That's possible. But in general, we would expect people with higher educational qualification to be of a slightly higher age group than those with lower educational qualification. I'm just guessing. Okay, so they could be related. So we need to figure out whether variables are truly related or independent of each other. That's something we have to study. Why? Because that brings in a complication. If x1 and x2 are related, and we put both of them in the equation, we might be counting the effect of x1 and x2 more than once, right? That's a possibility. Therefore, we need to take care of that issue. Another issue we need to worry about is whether they could be interacting. Okay, for example, people might feel sleepy. The probability that somebody will fall asleep at 8:30 in the evening is something. The probability somebody will fall asleep when Rajan is taking a class is something. But when both of them, Rajan is taking a class and it's also 8:30 in the evening, okay, then the probability might not be just addition of them. It could be more than that or less than that. Okay, so it might be interacting. The two variables, Rajan taking the class and the time of the day, they might be interacting, right? Another very funny example we used to give is, hydrogen is a very light gas. So you fill a balloon with pure hydrogen, it will go up. No, it will rise. On the other hand, you take air, which is predominantly nitrogen, you heat it up, okay, so it becomes a hot air balloon that also floats up. But then you put hydrogen in the balloon and then heat it up, everything falls down because hydrogen combusts when you heat it up, right? Interacts with the oxygen, it bursts. So the interaction between these two, hydrogen, fire, Put them together, the effect is completely different. Independently they give some effect, but together they give a completely different effect. It could be something like that. So that interaction term is something we need to study. Interaction among variables. Okay, that's something we might have to study, right? So these three are major challenges when we have more than one variable in our model. However, certain things remain the same. What? The measurement of the outcome variable. It's still y hat is some function of the x plus some error. The assumptions about the error, they do not change. What is it? The errors come from a normal distribution with mean 0 and a constant epsilon. That means all the measurements are made independent of each other. All these things valid. That means independence of measurements, assumption of linearity, the zero centration of the errors, then homoscedasticity, all these things are valid. The assumptions still remain the same, right? And then there are no outliers. That's another assumption, or we'll have to check for the outliers. Okay, there are no outliers, or we check for the outliers. How do we check for the outliers? Again, we will have to do all the leverages for each point, okay, for each x variable, put them all together, then y variable or prediction values, that's the studentized residual, then Cook's D, all these things we'll have to do. Okay? So the model diagnostics remains the same, but the building the model itself is slightly different because of these three challenges. Otherwise, it's the same. Okay. And remember, for a simple linear regression, we could use the formulas for beta naught and beta 1. Beta 1 is equal to rho sigma y by sigma x, or standard deviation of y divided by standard deviation of x. And beta naught is equal to y bar minus beta 1 x bar. That the formulas we can use, but when you have more than one independent variable, formulas are not easy to come by. They are very difficult, and therefore we resort to numerical computations. Okay. In terms of model diagnostics, is still the same. R squared makes no sense. Therefore, we only stick to R squared adjusted R squared value. That is using the mean squared error over mean squared total. Okay. And F statistic, again, we will not use the sum of squared residuals and sum of squared regression, but rather mean squared regression and mean squared residuals. But otherwise, the interpretations are the same, because R squared lies between 0 and 1, and F statistic is greater than 1, same thing happens. Okay. I have said the demo using delivery times with 2 independent variables. I am not sure I have that. Let's check. I have to search in my collection. Groceries MLR. Here it is. Okay, let's check that. I do not know what this data is. A number of items. Okay, so I have this thing as number of items. So 2 variables. Original data, as I told you, it was in feet. Okay, in the book, in the textbook, it's given in feet. But I have so I have, for my convenience, being not in North America or not in the US, I converted the unit to meters, but whatever it is. Right? So how do we build this? No, let me redo this. So this is the model building is still the same. Nothing changes. Okay. So this is the model. That is the time to deliver is beta naught plus beta 1 x1, where x1 is our distance, and then beta 2 x2, where x2 is the number of items to be delivered. Okay. So let's try to see whether if there is anything that comes up here. Okay. So let's go to data, and go to statistics, do regression. This is what usually we do. You do the independent variables. So that means what we will do is we will select both these columns, X1 and X2 together. Okay, so that way this system will understand we have two columns we have selected, so it will know that there are two independent variables. And then for the dependent variable, of course, we'll go select our Y column. Here. And then both X and Y have labels. Go here. And what do I want? I want the results to be printed here. And I go check here. Alpha is 0.05. Calculate residuals. I'm not going to be worried about residuals. Should I force the intercept to be 0? No, need not. Okay. Technically, it should. Okay. If you want, we can do that. Or if for the time being, let's not do that. Okay. So click OK. It spits out something. Okay. So you can see that adjusted R squared in our case has become 96%. Yes, Prince Dubey, please go ahead.
That you close the not equals to 0. So this is what exactly that? Basically, it is asking the B0. You mean?
Yeah, B0 is the constant.
Okay, so so the option that you chose into that window, is that denoting the B0 in that?
Correct. I did not choose that. See what happens
Okay.
is, if you go and select here, if you look in here, it will say force intercept to be 0. That means this intercept is a term for beta naught.
Yes.
In this case, B0. I did not select that. Okay. In fact, we can do that. Let's do that once. Let's repeat this because we know what it does. So let's repeat this once again. Okay. And go here. Let's take this Y. Okay. And then both of them have yes. And where do I want the results to be printed? I want the results to be printed, let's say somewhere here. Okay. And let's force, I don't want the residuals. Let's force the intercept to be 0. And let's see what happens. Okay, let's compare these two models. Okay. That's good. Adjusted R squared. Okay. As you can see, right? So both models have a very good performance in terms of the adjusted R squared. The model where we have forced beta naught to be 0 has a better performance in terms of adjusted R squared. How about the model itself? Did the model do better than no model prediction? Yes, of course. In both cases, right? So let me go here and increase the number of decimal points and see. Okay, practically 0. Now, how many zeros are? Oh, it goes on and on. Okay, so let's make it much bigger and let's see what happens. Okay, it's practically 0. Okay, so I do not know what that number is. Okay. Now, so that might be up after 25 decimal points. I do not know. Okay, so the model is also agreeable in both cases. Okay, in both cases, the model is also agreeable. And look at the coefficients. Okay, coefficients. Look at the p-value for all the for the original model where we did not force beta naught to be 0. The intercept was 0.0383. Remember, initially it was like 4.8 minutes, 4.8. Now it has come to practically 0. Sorry. Oh, sorry, that's a p-value. Statistics is here. 2. It is 2 minutes. Earlier it was 4.8 minutes. Now it's 2.2 minutes. So the more when you bring in this number of items, that now has reduced this value to be less than half of what was earlier. Okay. So these are the I'm sorry again. This is T statistic. Here are the values. Sorry. Here are the values. 2. It was 4 initially, 4.8. Now it's 2.4, almost exactly half. Okay, this one has changed again, and this one is new one. When we forced the intercept to be 0, which we have forced, okay, let us see what has happened. Okay, the p-values again, they are all less than alpha. Okay, and here are the numbers that we have. Okay, fairly similar, 0.01 for x1, 0.017, very similar numbers, 1.58, 1.67, slightly different. No, so maybe since this one, see, in terms of this initial diagnostics, both models look great. But since the second model, which has a slightly better R-squared value, we would be tempted to use this model. Okay, so that's the case. Then what you have to do, you will have to go and check whether in both of these models, you have to go check whether the all the assumptions, okay, and the outliers, all of these tests, which of these models pass. If both of these models pass all those tests for assumptions and also the outliers tests, okay, that is no outliers are present and all the assumptions are valid. If that's what you find, then which of these two models should be used? That's a very important question. And this is where we use the principle of what is called Occam's razor. Okay, use the model with the lower number of parameters. Okay, and this is going to be the guiding principle when you have two models which are performing fairly equally. Okay, so this will be our guiding principle. So I'm just showing this example essentially because in terms of building the model, there is nothing different from what we used to do before. So there is no great new knowledge here. Okay, okay. Let me save this with today's date. This is 05/04/2026. Okay. Okay. Now, how do we deal with categorical variables? Okay. And one person, I do not know who it was, one person already mentioned that we can use some kind of a coding. That is, for each category, we give a numerical value. Okay. Say, from that, we held on to that thought and we said we will give 0 for men and 1 for women in the gender example, right? So how do we deal with these categorical variables in general? In general, the most common technique that we use with categorical variables is that we use what is called dummy variables. Okay, we use what is called dummy variables. Let me explain what are these dummy variables. Dummy variables are binary variables, like gender in our previous example, 0, 1. Okay, or whether you pass the test or not, 0, 1. Right? So something like that. So binary variable, that means it has only 2 outcomes. If there are n categories, we are going to create n-1 dummy variables. How? here's an example. Let's see how we do this. This technique is called one-hot encoding. Okay, one-hot encoding. Okay, so what do we do? Here is an example where if a survey questions ask about the region of the country your office is located, with only 4 options: north, south, east, and west. Okay, so somebody writes north, somebody writes east, north, south, west, west, east. So that's what people give us the option. So there are 4 categories for this variable called region. Okay, there is a variable called region which has 4 categorical possibilities. Now what we do is we don't use this variable region, but we create new variables. In this case, I'm creating one variable called north, one variable called west, one variable called south. Okay, and when somebody is in the north region, then the variable north gets 1 and other 2 variables get 0. Okay, if somebody is in south, the variable south gets 1, the others get 0. Likewise, if somebody is in west, that variable gets 1, the other 2 variables get 0. However, when somebody is in east, we do not have a variable for east. Why? Because if somebody is in east, all of these will get 0. Okay, so if there are n categories, n minus 1 binary variables are sufficient to completely denote the data. Okay, so this kind of
Professor,
yes, go ahead.
Do we have any rule to choose the n minus 1 variable? And the second question is, if you choose this instead of that variable, is it make the outcome different?
No, the outcome will not be different. The model might look different. The parameters will look different, but the predictions will always remain the same. Okay, that's a very tricky.
Thank you.
Okay.
So you just to choose randomly, right?
Yes, you randomly assign. No, I could use north, west, south. You could use east, west, north. Somebody can use east, west, south. Okay, so anything could be, any of these 4 combinations could be possible, and all of them will give the same predictions. The parameters of the model might change, but the predictions will remain the same. Okay, so what is it that we are doing? Okay, so this is okay. Let's take a look at an example in this case of how to deal with this. Okay? Let's take a very silly example. There is something called salary data. Yeah, salary data. So let me save it as today's date. Okay. So here is data. Again, this is a contrived data. These numbers are randomly picked out numbers. Okay, and these are randomly assigned. So it's a contrived data. So don't worry about the validity of the data. But this is what this is just a demonstration, right? Say for example, this is a very egregious example where the salary is our y variable. This is what we want to predict, and we have 3 independent variables. One is gender, the other one is education, and the third one is experience. Right, these 3, all 3 in our case are categorical variables. Okay, now gender has only 2 categories in the data, male and female. Okay, so what I can do is, for gender, instead of gender with 2 categories, okay, I could create a variable called male. Okay, so what will happen? This will get 0 if the person is male. This will get 1 if the person is female. Right? So let me go ahead and put it here. Okay, male is the variable I'm going to use. Then, if you look at the education, there are 4 categories: graduate, higher secondary, postgraduate, and then high school. Okay, high school, higher secondary, graduate, postgraduate. I could use any one of them. Let us say I'm using high school. Okay, high school. Then let us say graduate, and then postgraduate. Okay, randomly, I'm just randomly choosing these variables. Okay, so if a person belongs in high school, for example, the first person, this person is a female, therefore the male will get a value 0. Okay, and the first person's education qualification is graduate, therefore graduate will get 1, the other variables will get 0. Okay, and then in terms of experience has 3 categories: fresher, low, medium. Okay, so I can randomly choose 2, so I can do low, medium, right? You could do fresher and medium. Okay, whatever you want to use. So for this person, let me see what this person's experience is: low, therefore low will get 1, medium will get 0. This is how I will one-hot encode each of the categorical variables. So to denote the different categories, let me color each one separately so that we know we are dealing with different categories. Right? So 3 different variables where we have done one-hot encoding. Okay, so this way you can create the entire data set, and then you have Y value. Then how will we go ahead and build the model? Okay, I have done one-hot encoding. So what do we do next? Next, what you do is you treat each one of these variables as though they are continuous variables and build a linear regression model. Treat them as continuous variables and build linear regression model. This becomes much more meaningful when we have one more data. Okay, not the salary. I'm going to check for another example. I do not know what that is. Okay, let me check this salary. Yeah, let's do this. I have age also added in here, let us say. Then this becomes very interesting. Okay, so in this case, then we'll treat all of them as continuous variables and then build the model straight away. Okay, and this is how we deal with categorical variables. This technique is called one-hot encoding technique. This one-hot encoding is very useful only when the number of categories is fairly small, right? Say here you have one variable. Now you have created 3 variables. Dealing with 3 independent, these are truly independent, right? Because if one is north, that person cannot be west or south or east, right? Therefore, these are truly independent variables. Dealing with a few independent extra variables might not be a difficulty. But let us say you are dealing with data. Let's say you are a HR. You are looking at some HR data, okay, personal data of a multinational corporation, and let's say they have offices in different countries, and in each office, people from different countries come and work. Okay, so let us say It's not, it's recoding. It's not an error, it's recoding only. So let me put it here. Okay. So let us say if we have people from 120 countries are working in the New York branch. Okay. Then if you want to do one-hot encoding for that, you just want to state which country this person is from or country of citizenship, right? And let us say you have 120 different values. These are categories, right? It's not a continuous value, it's a categorical value. Then if you start doing one-hot encoding for that, that becomes disastrous. In the place of one variable, now you are creating 120 variables. Your data set blows up, right? We don't want to do that. Okay. So when the number of categories is small, what do I mean by small? It's subjective. It's up to you. Okay. Usually I will say probably about a dozen or less. Okay. But when the number of categories is large, then we use other kinds of techniques, okay, where we might use different kinds of coding, where you can just give numbers like 1 is US, 2 is Canada, 3 is Mexico, so on. Randomly you give numbers and then treat that as a continuous variable, but that has issues. Okay. But then what you can do is you can kind of think of you can do some other thing, namely there is something called mean encoding. Okay, there is something else called, okay, I'm going to think of each country to be represented by a vector in some 5-dimensional space. Okay. Then I'm going to somehow calculate these vectors and use that. That's some very weird kind of encoding, right? Very many different techniques of encodings are available. This is one of the simplest ones. The other kinds of encodings, now starting from mean encoding and vector encoding, all these things you will learn in the next course called deep learning. Okay? That's when you will use. In fact, all our LLMs, what we call as language models, or these big models that we are fascinated with usually, all of them use this vector encoding. Okay, say for example, when you would have heard about terms like tokens, and then tokens are encoded. Okay, when you talk about that, what do you mean by encoding that? We imagine that each word or each token is represented by a vector in a 100-dimensional space. Okay. Therefore, each token, different tokens will have different vectors representing them. Okay. And that's one kind of encoding. How do we determine the vector? That's a different procedure. That's the separate procedure for determining those vectors. We have to ensure that a vector is unique for one token. Okay, and that's how the large language models are built. Now you have to first encode the words or tokens. Okay, so that's a different ballgame altogether. For our purposes, we will deal with one-hot encoding. Okay, so that's one issue. So that's taken care of. Just once you have done the one-hot encoding, treat these one-hot encoding variables as continuous variables and go build the model. No big deal. The next thing is interactions. As I told you, a variable, two different variables, when they are present by themselves, might have some effect. But just the presence of the other variable could bring additional effect. Additional effect. Additional means, please don't imagine it's only increased. It could be decreased also. Okay, some extra effect occurs. Okay, and one of the examples we used to give is another example. I gave you a couple of funny examples. A very serious example. if there's anybody from the pharma or medical side, you would know that. Usually, when people with asthma, they take some inhalers. They take some inhalers that helps the lungs to dilate, expand, and breathe much more easily. Okay, depending upon what kind of asthma it is, we will get these different kinds of inhalers. That's one issue. So this drug, okay, by itself helps expand the lungs so that people can breathe properly. When people get bacterial infection, say some kind of bacterial pneumonia, okay, then they take some antibiotic. What does antibiotic do? When you have pneumonia, that means the lungs are getting clogged up, okay, and then by mucus and other things, and then what happens is the antibiotic goes and kills the bacteria, and then the lungs become free. Now again, the person can start breathing properly. Except that when they take this antibiotic and also take this this inhaler, okay, the effect goes down. Together, when they take individually, each one has a positive effect. But then when both are taken together, the net effect is reduced. Why? Because these two interact with each other, and that brings in an additional effect. Okay, and that's a very serious interaction, right? In fact, you talk about drug interactions, and this is one of those classic examples. Okay, yes, Sam Young, please go ahead.
Is this where interaction means human decision making starts to break down when there's interaction, and AI decision making can, or AI assisted decision making can outperform? Okay, let me phrase it again. Can AI assisted decision making outperform human decision making because you have interactions variables?
I don't want to get into that idea of AI decision making, because we are at the very, very elementary level of machine learning. And as I told in the very first session, machine learning is a small subset of AI. So I don't want to extrapolate that much. But again, I'm not going there. The thing is that when two variables are present, then there is an interaction that is possible. How do we model the interaction? That's my only concern. How do we model the interaction? Okay. And that question I'm going to answer by using this second equation. Originally, this is what we have, two variables by themselves. But when the interaction is present, the interaction is always modeled as a product of the two variables, x1 and x2. Okay. When beta 1, 2 is 0, when this coefficient is 0, then there is no interaction. When this coefficient is negative, then overall effect is reduced. When this coefficient value is positive, the overall interaction effect is increased. Right? So that's what we are talking about. So I model the interaction of these two variables by using this term called this product. Okay. So let's take a look at another example. Okay, let me control stock data interaction demo. Yes, this is a very interesting example. Let me save with today's date. Don't ask me why someone would do this. The example I'm going to show, why someone would do this, don't ask me that. This is a demo of interaction ideas. So with that in mind, let's see what we are doing here. Okay. So we have three stocks. Okay. Stock 1, stock 2, stock 3. Okay. And what I want to do is, I want to predict the value of one stock based upon the value of the other two stocks. Okay. Why? Maybe I think that this could be done. Okay. Say for example, if the stock of fertilizers and the stock of gunpowders, values of these two increase, then my price of onions might go up. I do not know. There could be some reason to believe this. Okay, whatever it is, or these might be coming from the same business house. Okay, three different stocks from the same business house, and maybe I therefore expect that there might be commonalities in terms of policies, decisions, whatever. Therefore, they might have some similar behavior, or therefore I can model one based upon the other two. Something, whatever reason. Okay. So let's say I want to build a model of this stock one based upon the models, based upon the values of these other two stocks, X1 and X2. And I have already built the model. Okay. So here is the model. So stock one value is equal to a constant beta naught plus beta 1 X1 plus beta 2 X2. That's the model I'm trying first. Look at the adjusted R squared value. Okay, here is the model. Right? Here's the model. So look at the adjusted R squared value. Okay. How much is it? 0.38. Only 38% of the sum of squared totals is corrected by the model. Okay, so maybe it's not that great a model. That's okay. Maybe there's too much variability in the data. So let's look at the model's p-value. P-value is less than alpha, right? P-value is less than alpha. Okay, therefore the model probably is usable. Great. How about the parameters? Let's go take a look at the parameters. These are the parameter values. Okay, and let's see whether each one has a good p-value. That is p-value less than alpha. That's what we want to find. Why? Because the null hypothesis is each of these parameter value is 0. That's the null hypothesis. Therefore, when p is less than alpha, we reject the null hypothesis. Let's go check. For the constant, for beta naught, p is less than alpha. Therefore, that's okay. So we can we reject that null hypothesis. Therefore, we can use that intercept value. But for the beta 1 and beta 2, okay, look at that. Both are much greater than alpha, which means we cannot reject the null hypothesis. What is the null hypothesis? Beta 1 is 0, beta 2 is 0. We cannot reject that. Essentially, neither of these two stocks have any influence on the stock 1, but the model is good. What is happening? Something weird is happening, right? Even at least one of them, if they had p less than alpha, maybe I could have dropped the other one and did this, right? But the model is good, but both of these parameters are statistically 0. So what do I do? This gives me an idea, something weird is happening. So what do? I try an interaction model. So I bring in a new variable called x3, okay, where x3 is nothing but x1 times x2. That's all, right? So x1 times x2. I bring an interaction term. Okay, I bring the interaction term, and both are 36, 35. Okay. Okay. Now let's build. So now we have three variables x1, x2, x3. Right? We have three variables x1, x2, x3. Okay. Control C, Control V. I want to make yes. And I have 3 variables and build the model for this. So this is the model I'm going to build. Okay, so let's build this model. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Let's look at adjusted R squared. I built the model. Building the model is just pressing that button, right? So don't worry about going and dragging and dropping all these things. So I built this model. Look at the adjusted R squared. It has almost doubled. Earlier it was 0.38. Now it's 0.75. So bringing this third variable, right, which is nothing but the interaction term, has improved the performance. 75% of the sum of squared totals is now explained by the model. Excellent. How about the p-value for the model? P-value for the model is also awesome. Much less than alpha. Right? It's much less than alpha. So model is also good. How about each parameter? The parameter values are here. How about this hypothesis testing on these parameters? Okay, let's take a look at it. Now, if you see the p-value for the constant beta naught is greater than alpha. Therefore, we cannot reject the null hypothesis that the intercept is 0. So the intercept is now has to be taken out. Now look at the other variables, beta 1, beta 2, beta 3, the coefficients of the variables. This is interesting, right? The coefficient for the first stock is agreeable because its p-value is much less than alpha. The coefficient for the second stock is not agreeable because it's much greater than alpha. So we cannot reject the null hypothesis on the second variable. What is the null hypothesis on the second variable? That its coefficient is 0. That we cannot reject. But look at this, the third one, the interaction term. This we can reject the null hypothesis. So what does it mean? It seems like the x1 is important. The first stock, its value is important. The value of the second stock is not important. But the interaction of the second stock with the first stock is important. Right? Very weird situation. Let's check that out. Let's check that out. Right? So I am checking that out here, the third model. What is this? I'm checking whether I can build a new model for that y with only the values of the first stock, stock 1, and the interaction term alone. I can put it. Why? Because it's like a new variable, that's all. Right? So when I do that, what happens? I build the model. So this is the model I'm using. Adjusted R squared remains fairly same. It was 0.75, now it's 0.72, slightly worsened. Okay. How about F value, the F statistic? This is still awesome. This is still awesome, right? So now it is still the model is agreeable. Look at the coefficient values. They are something, whatever that means, doesn't matter. Look at the hypothesis testing, right? Now, like what we predicted earlier, the intercept is still, we have to reject, we cannot reject the null hypothesis on this. The intercept is still not different from 0. But the coefficients of x1 and the interaction term, they are different from 0. So we can go ahead and build one more model. Okay, we are using the same data. Let's do that here. Here I have done that. Okay, do with the same data, build one more model where we force the intercept to be 0. Okay, when we do that, look at what happened to the adjusted R squared. 0.99. Okay, look at the model validity, F statistic p-value, practically 0. Look at the p-value for the coefficient for stock 1 and the interaction term, practically 0. So the final model that we have to work with is y is equal to beta 1 times x1 plus beta 3 times x3. So this is the model that we will have to work with for this particular data, right? So let me make it yellow and let me make it this thing, right? So this is how sometimes we will have to deal with identifying the correct model. Okay, so this is a very egregious example on interaction, how interactions could become a headache. Okay, very simple data. Look at what we have. How many? We have only about 15 data points or so, right? How many data points are there? Yeah, 3 to 17, 15 data points. Okay, but among this, you see how many iterations we have to go through before you end up with the good model, mainly because of the interaction terms. Okay, I'll stop here. Somebody asked a question. Please go ahead, ask your question.
Professor, when we go with a MLR problem solution, for example, like the assignment problem, we might have tried many things, and we will finally settle with one. In that case, only the whatever we find that working, only that need to be documented, right?
That needs to be given as a solution.
Okay.
But I would suggest that you also write up somewhere how you arrived at the solution.
Sure. And one more thing, Professor, when we want to calculate the row in case of the feature selection for a MLR problem, and kind of a correlation coefficient and all those things, like we might do a Python analysis and so on, which is external to the ML Studio, and we can bring those images into the report, right?
Yeah, you can do that. You can do that.
Okay. And one more question, Professor. Now, you were mentioning about this interaction where the multiplication of two variables. Now, can there be any other relation, like a power relation or some kind of a 2x1 plus x3, something of that sort, a kind of a convoluted one?
No, no. Interactions is always modeled as a product.
Okay, okay. And
it's a model, right? So we just use this product as a model.
And what we will do is, like, we will try that when we bring in those interaction variables, whether it is improving or not, we will check that, and then we will decide, right?
Correct.
And another thing, Professor, like when we see that two of the variables in the MLR, they have a higher correlation, let's say 0.6 or something. Now, what is the threshold point where
Muhammad, yes, we have not come to the point of correlation between these two variables. That's the next topic.
Sure.
Immediately after this topic.
Sure.
Okay. So, if possible, we can finish it in the next 10 minutes. So, before moving on, so interactions we are done. We are done with interactions. Now, what we need to do is, let's think about more than two variables. Let's say three variables. Okay. Then we have lots of interactions. x1, x2, x1, x3, x2, x3. And also x1, x2, x3, all the three interacting among themselves. Okay, all these are possible. Okay, when you have three variables, only this many, x1, x2, x1, x3, x2, x3, x1, x2, x3, only four interacting terms. But when you have four variables, this becomes complicated. x1, x2, x1, x3, x1, x4, x2, x3, x2, x4, x3, x4. These are all pairwise. These are called paired interaction terms or first order interaction terms. Then you can go for the second order, triplets, x1, x2, x3, x1, x2, x4, x2, x3, x4. Then the second order or third order now, x1, x2, x3, x4. Lots more interaction terms coming. If you have 10 variables, now you can see the kind of complications we are going to have. Okay, therefore, while theoretically we need to check all interactions, okay, what we do is this. If interaction terms have to be included, use only the first order interactions, that is pairwise interactions. Even if you have 20 variables, you only do x1, x2, x1, x3, x1, x4, x4, x5. No, only pairwise interactions. Don't do more than two term interactions. Okay, that's the universal guideline. Okay, that's the take-home message. Okay. Now, should we do interaction terms? Let's say you have a data set. Now, if you have worked with clinical data, you might have seen, no, we have about 20 variables. Should we look at all these pairwise 20C2 interaction terms? Should we include them in the model? Theoretically, yes, but we say no. Okay, why? Basically, because bringing in more variables usually makes your model perform artificially well. Okay, so what you have to do is you have to first use your domain knowledge. When you have too many variables, you have to use your domain knowledge to see that whether interaction between some variables are possible. If your domain knowledge says that, then include them. Otherwise, if the number of variables are large, don't use interaction terms. See whether your no interaction model itself works good, well enough for you. That's a keyword. That's a catchphrase, right? If the model works well enough for you, good enough for you, that is, if its predictions are within your tolerance, go ahead and use it. Why complicate it more than what is necessary? Okay, so that's the usual approach we take when we deal with large number of variables. But this is something that you have to keep in mind. If there is a, if theoretically you know that two variables interact, then you must include them. Okay, so with that, we'll stop with interaction terms. This is what I was talking about. Okay, the final idea that we want to talk is, okay, we have 5 more minutes, so let's get on with it. Okay, so it's a short topic. If two or more variables are related to each other, that's what Mohammed was talking about. Mohammed Niaz was talking about, right? Let's say we have k variables in our model, and let us say I'm going to tell you what is the problem here. Okay, so back with the mathematics, x2 and x3 are related. Let's say in this equation, x2 and x3 are related. That is, we find the correlation between x2 and x3, and the correlation is high. Let us say, if that is the case, then from our previous simple linear regression, we know that we can write x3 as a linear regression of x2, right? Or we can write this term beta 3 x3 as some constant plus some other constant time x2. So instead of beta 3 x3, I can write this expression here. Right? Instead of beta 3 x3, I write beta 2 0, beta 2 1 x2. Okay. Therefore, what happens? This equation will not have beta 3 at all. Sorry, x3 at all. It will only have x2. Right? So finally, I will have a model that will, I should have a model, not I will have, I should have a model which will be like y hat is equal to some constant plus beta 1 x1 plus beta 2 x2 plus beta 4 x4 without any beta 3 x3. Right? Because beta 3 is related to beta 2, because x3 is related to x2, the effect of x3 is absorbed in the coefficient of x2. So anyway, we are going to find this coefficient. If you again put beta 3 x3, what is it we are doing? We are inflating the effect of this variable. Right? We are inflating the effect of this variable. Therefore, this is something we need to be worried about when we have more than one variable in the model. How do we ensure? So the key idea is this. The key idea is this. bear with me for 5 more minutes. Let's finish this. This very easy idea. Okay. Because you know all the foundations for this. So let's take a look at it. Okay. We define a quantity called variance inflation factor. Don't worry about it. The idea is this. We start with the assumption that every variable is related to every other variable. Okay. We start with the assumption that every variable is related to every other variable. So x1 is related to x2, x3, x4, xk. x2 is related to x1, x3, x4, xk, so on and so forth. Okay. Now we build these models. So you can go ahead and build these models. No, assume that now these are independent variables for this model. So build these models, and when you build these models, what do you get? You get R squared for each one of them. That is adjusted R squared. Okay. So for the first, for x1, you will get some R squared. For x2, model for x2, you get some R squared. So on and so forth. Okay. Now here is where the key is. If the R squared value is very high, then what does it mean? That means that is a good model, right? Whatever be the variation in x1, this model is able to explain that much of that variation. That's what R1 squared tells you. R squared tells you. So what you do is look at these R squared values and see whether these R squared values are high. So whichever variable has a high R squared value, you know that that variable can be absorbed into the other variables. That variable can be absorbed into the other variables. Therefore, drop that variable from the model. That is the idea. Very simple idea, right? Of course, now statisticians, if only they let us live happily like this, then they wouldn't have a job. So some statistician came up with a better idea. Let's use some quantity called variance inflation factor. Variance inflation factor is nothing but a quantity defined like this: 1 over 1 by R squared. 1 over 1 by R squared. Okay. So for each one of these things, each one of these, you can calculate the variance inflation factor for each one of these models, right? Then you set a threshold on VIF. Okay. A variable with VIF greater than 4 is said to be dependent on other variables, or it is called multi-collinear with other variables. So you calculate the VIF for each variable, each x variable, and see which one of them have variance inflation factor greater than 4, VIF value greater than 4. You identify those variables, throw them out from your model, use the remaining ones. And this way you can ensure that the variables that are there in your model are independent of each other. So this answers the question that Muhammad Niaz was asking. Now, how many correlations should I be looking at? Okay, this technique will answer that question. Okay. So we will take a look at this. Okay, we will take a look at this demo tomorrow when we come back. No, maybe not. Let's finish it off. Okay. Let's finish it off. Oh, I have too many data sets.
Let's finish it, or we will forget it tomorrow.
Let's finish it. Yes, it's a very simple. I'm not going to finish it. Actually, I'm going to leave with a very uncomfortable question now, because we are going to find something very interesting. That particular data, that's the real data. Okay, so that data is going to show you something very interesting. Empty cars. Okay, let me open this. I do not know which one is which. So let me open one of them. Yeah, I don't want any of this. So what I want to do is, I want to build, let me put in a insert of column before. I want to build a model for the fuel efficiency based upon all other variables. Based upon all other variables. Okay. So now let me go ahead and do that. I'll put it here. Okay, somewhere here I'll put the results. So go model statistics, regression, independent variables from here. Here. Okay. And the dependent variable. Last column. Yes, they do have and results. I'm not going to force the intercept to 0 because there are too many variables. I do not know whether it should be 0 or not, so I'm not going to force it to 0. Results I want to place here. So let us say and say, okay, go. Okay. So look at the adjusted R squared. Very good value. Look at the model p-value, you know, the ANOVA, the model p-value, practically 0. The 4e minus 0.07 means 4 times 10 power minus 7. That is 0.0000007, 004. That's what this p-value is. Okay. Now let's look at the coefficients. Okay, coefficients. Let's look at the p-value for this. Okay. Look at the p-values. None of them, including the intercept, none of them is less than alpha. Right? None of them is less than alpha. But the model is good. Okay. So now this is very similar to the stock example. At least in the stock example, when we started, the intercept was agreeable. But here even that is not agreeable. So what should we do? What we should do is probably, we would think first check the interaction. Well and good. Why? Because if the weight is high, you might think that the QSEC is the time taken to go from rest to travel at the fastest speed, travel quarter of a mile. Okay, that's the QSEC. Okay, maybe these two are related. Okay, maybe the displacement of the cylinder and the horsepower are related. Right? Maybe the number of cylinders and the horsepower are related. Who knows? Right? So we can imagine immediately that some of these variables might be related to each other. Therefore, in this case, we have to do VIF, variance inflation factor, for each one of these variables. Unfortunately, Excel and tools like that do not do VIF. Of course, Python, you can do that. In R, you can do. And Azure, you can do. Basically, because in Azure, you can bring in your own Python code. You can import your Python code and do it there. It's possible. So you could do it in Azure too also. So if you can do that, go check it out. Okay, check for the variance inflation factor. You will see that only 2 or 3 variables are actually truly independent. The others are all dependent on each other. So there is heavy multicollinearity in this data. Okay, and so I'm going to stop here. We are already quite a bit far into the beyond the session time. So I'll stop here. What we will do is next session, when we come back, we will look at other methods. These are standard methods. There are a few other methods that we have to deal with these kind of issues. Okay, I'll stop here. Yes, Mohammed Niaz, please go ahead and ask your question.
Yes, Professor. So our first assignment is on the MLR, and we are midway through. And our next session is tentatively scheduled on 10th, subject to upgrades approval. Now, would it be possible to give a couple of days, at least 12th or something, so that we will have a complete awareness of MLR and apply it on the assignment?
That is definitely possible. Do me one favor, Mohammed Niaz, please send me an email reminding me of this. Okay, I will write to Upgrad team to push the date by 1 week.
Sir, again, sorry to interrupt. I'm literally very happy that you're all very interested, but we are all working colleagues and we have a couple of business travels quite often. So unfortunately, I cannot commit any days on this week. Could you please consider for next week? It is a sincere request, Mohammed Niaz. I'm completely agree that you want to finish the assignment 1, but it's not our plan. So I plan to learn, not only for assignment. So could you please kindly make sure send to Upgrad? In the poll, is not everybody answered also, is it? Could you please make it on next week, as we already requested 17th, or maybe you can say week later? Yeah, it would be very nice. Sorry, Rajan sir, it's important for us to understand, then finish the assignment. Yeah.
I told you that I don't have a problem with any date. I have no issues with any date. It's okay. So you come to a conclusion, consensus, and tell me, and I'm very happy to accommodate any date. Okay. If the verdict is split, let us say somebody want only on the 10th and somebody want only on the 17th, I am ready to repeat. No issues. Okay, no issues. You please come with a plan. Okay. So that's my point. So you please discuss among yourselves, and for to be fair, we can push to 17 if it needed. I have no issues. So please, you iron things out among yourselves and let me know.
Thank you, Rajan.
Okay, I have lots of Excel to upload today. I will do that. Okay, and I'll stop here. Okay.
Professor, one more question.
Yes.
When I give the mail, Upgrad will not consider it as a personal extension request and subtract, because for the entire course only 4 extensions, something of that sort, right?
No, no. You see, you can say that you have discussed in the class,
okay,
and you have discussed with your classmates through WhatsApp, and this is the decision that was taken collectively, and she see me on that.
Sure.
Okay, and usually they will anyway come back and ask me. So CC me on that.
Okay.
And for your benefit, let me type down my email address.
Sure.
Insights.com. This is one. That's another one. Either one is fine. Upgrad has both of these emails, so you can CC either one. Okay, great.
Yeah, thank you.
Okay, thank you all. I hope
Thank
you
you.
all had a great weekend. If the weekend is still there, for some of you, enjoy the weekend. I'll see you next week. Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Thank you.